For some reason, when you see an old wooden sailing ship moored in a harbor, it appears incredibly solid to us. Its thick side walls, massive hull, and imposing lines evoke a sense of unshakable strength. Yet modern vessels are technically far superior to their predecessors in terms of structural integrity. So why do we get the impression that old ships were built to last forever? The answer lies at the intersection of engineering, design, and human perception. And that is exactly what we will explore in today's video. To understand this, we must first travel back to a time when shipbuilding was both an art and a science. For centuries, shipwrights shaped wood by hand, plank by plank, frame by frame. Every piece was skillfully cut, fitted, and joined together, leaving visible marks throughout the hull. Oak, teak, and acacia were favored for their natural density and resistance to salt water. Such massive timber gave hulls considerable thickness, sometimes exceeding 10 centimeters in larger vessels. When you placed your hand on these planks, you could feel the grain and weight of the wood beneath your fingers. The internal support beams forming the ship's skeleton were often visible from within the hull. You could see the structure, touch it, and immediately understand how the vessel withstood the waves. This structural transparency created a direct connection between the observer and the ship's solidity. The hulls of 18th-century sailing ships were so thick that they could absorb significant impacts. Planks were laid in double, sometimes triple layers, reinforced with natural timber curves known as knees. Every joint between two pieces was filled with linen fiber and pitch, providing an organic seal visible to the naked eye. Builders of earlier eras also used hardwood pegs that swelled upon contact with water to reinforce connections. This ingenious technique turned water, the sailor's natural enemy, into an ally of the structure itself. Large sailing ships had high, massive railings surrounding their decks like castle walls. Their imposing masts, carved from whole tree trunks, rose toward the sky with an almost monumental verticality. The standing rigging, composed of braided hemp ropes and supports, framed the space with a powerful geometry. Every visible element of the ship conveyed an undeniable impression of strength and endurance. Now, let us compare this with a modern fiberglass vessel fresh from a contemporary shipyard. Its smooth, uniform, and gleaming shell reveals nothing about its internal structure. The thickness of its walls can be reduced to just a few millimeters in certain optimized sections. From the outside, this thinness can give the impression of fragility, of almost excessive lightness. Yet this thin, laminated composite layer possesses an extraordinary strength-to-weight ratio. Fiberglass impregnated with resin creates a material that does not rot under pressure, does not rust, and does not deform. Modern carbon or Kevlar hulls deliver structural performance that wood could never achieve. A composite sandwich construction with a high-density foam core can withstand significant bending forces. Yet all of this remains invisible, concealed beneath a perfectly smooth surface that betrays none of its resistance. This is precisely where the paradox in human perception of ships lies. Our brains instinctively associate thickness and weight with solidity, even when this relationship is misleading. A thick stone wall inspires more confidence than bulletproof glass, even if the glass is technically more resistant. This cognitive bias applies perfectly to the maritime world and profoundly influences our visual judgment. Old riveted steel ships also conveyed an impression of indestructible power. Every visible rivet in a ship's hull served as a production mark, bearing witness to the human labor invested. Steel plates assembled together formed a raw metallic mosaic reflecting industrial robustness. The straight, pointed bows of early 20th century cargo ships visually cleaved through space with great force. Compared to the modern bows whose curves are determined by computer calculations, they seem designed to overcome any obstacle. Low and stocky superstructures gave these vessels a visually reassuring center of gravity. Even as the ship rolled in stormy seas, everything appeared anchored, heavy, and immovable. Modern ships, by contrast, feature taller and more aerodynamic superstructures that can look vulnerable. Their wide windows and fluid lines suggest comfort rather than resistance to the elements. This aesthetic evolution reflects a fundamental shift in shipbuilding philosophy. In the past, engineers designed with survival as the primary objective, and comfort emerged almost accidentally afterward. Today, structural strength is integrated from the very beginning, from the digital design stage, long before the first component is manufactured. Simulation software allows every element to be virtually tested under extreme constraints. Modern engineers eliminate every unnecessary gram of material in order to optimize the ship's overall performance. This optimization makes the vessel more efficient, but also causes it to be perceived visually as lighter and therefore more fragile. Ancient builders, however, lacked this computational capability and compensated through an excess of material. They systematically produced every component in larger dimensions than necessary in order to create an empirical safety margin. This surplus of material was, in essence, a form of deliberate ignorance regarding the forces actually at work. Yet, paradoxically, this excess gave rise to an aesthetic of strength that continues to captivate us even today. The thick planks, massive fittings, and impressive rigging told a story of struggle against the forces of nature. Every visible detail of an old ship carried the traces of a constant battle with the ocean. The wear marks in the wood, the scratches in the metal, and the salt-formed patina lent credibility to this impression. An old rigging bearing navigation marks appears to have proven its strength by passing the test of time. This narrative dimension is profoundly absent in modern vessels that roll off production lines with flawless perfection. The construction technique itself has also played a role in this inherited perception of strength. The clinker-built construction, in which planks overlap like scales, created an impressive relief across the hull. Each overlap formed a shadow line that emphasized the physical presence of the material. The carvel-built construction, with planks joined edge to edge, offered a smoother yet still textured surface. Copper nails and wrought iron fittings added visual anchor points that accentuated the structure. On Viking longships, rivet lines undulated along the hull like the muscles of a sea creature. This organic analogy between the ship and living beings subconsciously reinforced our perception of its vitality and power. Spanish galleons with their enormous stern castles resembled floating fortresses crossing the oceans. The figureheads and gilded ornamentation on the bows of ships added a symbolic dimension of power and prestige. 19th-century sailing ships combined hydrodynamic refinement with visible solidity in a remarkable balance. While the sharpness of the bow promised speed, the wide and deep sides inspired confidence. This duality between agility and strength may represent the pinnacle of maritime design from a visual perception standpoint. Traditional wooden fishing boats, with their short and sturdy builds, embodied a form of functional durability. Their rounded shapes and wide freeboards allowed them to cope steadily with rough seas. Every mark on a boat's hull told the story of a fishing season, a gust of wind, or a hard landing. These traces of life gave the vessel an almost human identity, that of a survivor hardened by experience. None of these distinctive marks are found on a modern yacht built from pristine white composite materials. The perfection of the surface creates a distance between the observer and the structural reality hidden beneath. Yet, under that smooth surface, strategically placed reinforcements absorb shocks with tremendous efficiency. Molded composite beams distribute loads optimally throughout the structure. Watertight bulkheads divide the hull into independent compartments capable of preventing flooding. These invisible innovations make modern ships extraordinarily resilient in extreme conditions. Yet our eye, accustomed to seeking visible signs of strength, finds nothing to hold on to. Continuous welding on modern aluminum hulls creates nearly invisible and perfectly smooth joints. Compared to a neatly aligned row of rivets on an old ocean liner, it conveys no structural information whatsoever. A rivet clearly showed that two plates were firmly joined at precisely that point. Modern welding methods accomplish the same task often better in complete silence. This technical refinement, while an engineering triumph, represents a defeat in terms of visual communication. Ancient ships also used geometric shapes to intuitively express their strength. Deep U-shaped cross-sections gave hulls an appearance of tremendous solidity. Vertical, blade-straight bows appeared capable of cutting through any obstacle. Square, high sterns created a visual barrier against waves pursuing the vessel. Modern ships favor more pronounced V-shaped cross-sections to enhance their seakeeping abilities. While this shape is more hydrodynamically efficient, it appears sharper and therefore more visually vulnerable. The inverted bows of contemporary designs subvert our traditional perception of how a ship should look. Despite significantly improving their behavior in waves, they appear to retreat from the sea rather than confront it. The deck of an old wooden ship also offered a sensory experience that conveyed an unparalleled sense of solidity. Tightly fitted teak strips joined with black mastic created a warm and reassuring checkerboard pattern underfoot. Cast iron bollards, bronze cleating hooks, and wrought steel fairleads felt heavy in the hand. Every piece of hardware fastened to the deck seemed designed to withstand enormous forces, and often was. On a modern vessel, anodized aluminum bollards and technical plastic winches serve the same function. Yet their lightness and synthetic appearance do not evoke the same emotional response in the observer. A hemp rope 5 centimeters in diameter inspires more confidence than a synthetic cable 8 millimeters in diameter. Yet the breaking strength of the synthetic cable far exceeds that of hemp. Our perception remains trapped in an era when size and weight effectively guaranteed strength. Advances in material technology have completely separated appearance from actual performance. Structural foams, carbon fibers, and epoxy resins have redefined the rules of shipbuilding. 1 square meter of carbon epoxy laminate can bear loads that an oak panel could never support. Yet oak, with its deep grain and amber hue, speaks directly to the instincts inherited from our ancestors. As a species, we evolved by building with natural materials whose quality we could assess by touch. Dense and heavy wood meant strong wood, and this equation is engraved in our collective subconscious. Modern composite materials overturn this instinctive interpretation, leaving us in a state of uncertainty. This perception of superior strength in old ships also has a temporal dimension. The historic vessels that have survived to the present day are, by definition, the most robust ships of their era. Thousands of poorly built ships sank and vanished from our collective memory without leaving a trace. This survivorship bias leads us to believe that all old ships were exceptionally strong. In reality, shipwrecks were an extraordinarily common occurrence throughout every period of maritime history. The shipping records of major companies reveal loss rates that would seem utterly unacceptable to us today. Yet our harbor museums display only beautifully restored examples, telling an incomplete story of shipbuilding. This natural selection of memory shapes our romantic and biased perspective on ships of the past. Traditional maintenance practices have also contributed to the perceived longevity of these vessels. Regular caulking, tarring of hulls, and greasing of fittings were constant and visible rituals. These maintenance tasks ensured the ship's survival and reinforced the idea that it was a durable but demanding organism. A fiberglass vessel requires visibly less maintenance, which paradoxically diminishes our perception of its value. Its apparent effortlessness causes us to overlook the technical sophistication that makes this quiet resilience possible. And so, modern shipbuilding has simultaneously achieved something both remarkable and paradoxical. It has created ships that are stronger, lighter, and more durable than anything previously seen in maritime history. But in doing so, it has eliminated nearly all of the visual cues that allow our minds to perceive that strength. Ancient ships wore their power openly, like visible and reassuring armor across their hulls. Modern ships conceal their resilience beneath an anonymous surface that reveals none of their true capabilities. This evolution teaches us something profoundly important about the relationship between appearance and reality in the world of engineering. True strength does not need to be spectacular in order to be effective. Yet our human gaze will continue to seek the promise of visible power in forms and textures. Perhaps that is why the old sailing ships resting silently in their home harbors continue to stir within us a feeling that even the most efficient modern yachts struggle to replicate. That is all for today's video. Don't forget to subscribe to the channel and like the video for more content.